Today we're happy to have Hindy Drillick from Columbia University, who will tell us about the stochastic six-vertex model speed process.
Okay, thank you very much for the introduction, and I'm happy to be here. Just, I guess, one quick question: is there a clock anywhere? Otherwise, from at the end, I'll have to.
There used to be a clock.
Okay, no problem. Just we'll see when we get towards the end. Okay, so today I'll be talking about the stochastic six-vertex model speed process, and everything I'll be discussing is joint work with Levi Hauenschmidt-Sibitz, who's currently a postdoc at KTH in Sweden. So in the talk, I'm first going to introduce the stochastic six-vertex model, and in particular, we're going to be concerned with the notion of second-class particles. Then we're going to discuss the main result, which in brief is studying the speed of the second-class particle and showing that it converges. And then we're going to use this result to construct the stochastic six-vertex model speed process, which is what was advertised in the title of the talk. And finally, we're going to discuss some of the proof ideas to do this. So what is the stochastic six-vertex model? So the six-vertex model, without the word stochastic, is a discrete model from statistical physics that was studied originally by Pauling in the 30s to model two-dimensional ice. We're not going to see so much of that physical interpretation in the talk, but roughly my understanding is that if you're modeling ice crystals, then there's hydrogen-oxygen bonds, and they could fall into roughly 6 different configurations. And the model that we're going to be concerned with is a stochastic version of this model, which means that we can interpret it as a Markov process or an interacting particle system. And this was introduced by Grönspön, and that's the one I'm going to introduce in a minute. And I just want to mention that this model degenerates to many other models that you may have seen before, including the asymmetric simple exclusion process or the totally asymmetric simple exclusion process. It also has a scaling limit to some deformations of polynuclear growth. So it's a model that has, it's a well-connected model. And we're going to define this model on the discrete lattice. So here's what the model is going to look like. So as promised, we have 6 different configurations that could occur at a given vertex. And basically, we're going to pick 2 parameters, B1 and B2. These will be numbers between 0 and 1. And we're going to view the edges that come in from the left and the bottom of a vertex as the inputs to a given vertex, and the edges that come out from the top and the right as outputs. So I don't know if, could you see the pointer? Yeah, so in this configuration, you imagine you have 2 inputs coming in, and therefore 2 outputs come out because we want some conservation of the particles. So this will happen just with probability 1. In the second case, if there's no particles coming in, then again, deterministically, we're going to have no particles coming out. The more interesting configurations are if you have a particle coming in from the bottom, it will keep going up with probability B1, and with probability 1 minus B1, it will turn, which is this configuration. Similarly, if you have a particle coming in from the left, it will keep going horizontally with probability B2, probability 1 minus B2, it will turn. So what we're going to do is we're going to fix some boundary inputs. So these are particles that could come in from the bottom boundary or from the left boundary. And then we're just going to, we could start at the corner. We see 2 particles coming in, so 2 particles must come out. And we could kind of proceed then to these 2 configurations and so on, going away from the diagonal, and we could tile every single vertex with, one of these configurations. And this will give us a random configuration of upright paths on the quadrant, and it could be extended to the entire entire quadrant. In particular, in this talk, we're going to be concerned with the following initial data, which is called step initial data, where you basically have particles entering every row from the left and no particles entering from the bottom. So for example, this could look like this if you sample it. And an important object that we'll be concerned with is the height function of the model. So at position xy, the height function just records the number of particles that have already passed either through xy or to the left of xy. And it's, just kind of as you could just see the numbers here filled in, and it's pretty straightforward to define the height function for this model. Okay, so what does this model look like if you actually simulate it? So first we start with the case B1 larger than B2. So recall that B1, I'll just draw it here. So B1 is the probability of going up. Could everyone see what I'm drawing? And B2 is the one where you continue going to the right. So if B1 is larger, your model kind of has a preference to go up, and therefore all the particles will just stay packed above the diagonal. The second picture is actually a simulation, but I could have just put a black triangle, and maybe it doesn't look very interesting. The more interesting case is if you take B1 less than B2, and now the particles have a tendency to go more to the right and they actually spread out. And so in this simulation, I think I took B1 to be 0.3 and B2 to be 0.7. And you see that in the second picture, it's more clear. You know, there's a region at the top where the particles are still packed. There's a region at the bottom where it's empty. And in between, we have this region called the rarefaction fan where the particles are spreading out. Their density is going from 1 to 0. And in particular, the boundaries of this fan-shaped region are given by the slopes or by the lines with slope 1 minus B1 over 1 minus B2 and 1 minus B2 over 1 minus B1. Those give the upper and lower boundaries for the rarefaction fan. And because of this, we could already kind of see a hint that 1 minus B1 over 1 minus B2 is an important parameter of the model. And in fact, instead of parameterizing the model in terms of B1 and B2, we could parameterize the model in terms of the ratios of B1 and B2 and the ratio of 1 minus B1 and 1 minus B2. So this will come up a lot in the talk, so I put that here. And then in this language, the rarefaction fan are all the slopes between 1 over kappa and kappa. Okay, so the next thing we need to introduce is the same model, but we allow every particle to have a class. That's called the multi-class stochastic six-vertex model. And here I have two classes. So I denoted, so a class is an integer. So you could have first class, second class, third class, or really any integer class. And I have, let's say, the red lines represent particles of class I, and the blue lines represent particles of class J. So now when you have two lines coming into a vertex, the weights will depend on the classes of those particles. So particles with a smaller class, for example, a first class particle, will have higher priority over particles whose class is a higher number, right? So first class has higher priority than second class. So in the first picture, it's just the same as before because there's only one class and nothing, you know, just behaves like before. But in the other four pictures, we see that if you just ignored the blue particle, because that one has lower priority, if you just ignore it, then the red particle is actually just behaving like before. It goes up with probability B1, it turns with probability 1 minus B1. So what this is really saying is that you could sample the higher class particles first, and then the lower class particles behave in the same way, but they're restricted. They can only move along the edges that are still free after we already sampled the higher priority particles. We'll see a picture in a second. So just, this is what I said before. And also, if you imagine that, you know, in the original model, we had edges with particles and edges without particles. So you can imagine that edges without particles are actually particles with class infinity. So that's like the lowest possible priority. And then if you do that, then this would actually, if you took, you know, I to be first class particles and J to be infinity class particles, you would just recover the usual model. More generally, if you have a bunch of classes, there is some projection to get back to the original model. So you could merge all the classes together and view class infinity as holes or, you know, empty edges, and you would recover the original model. So maybe to make this more concrete, I'll talk about the case that we're going to be interested in, which is the case where you have step initial conditions. So all the black lines are the step initial conditions that we had before, and we could view all of those as first class particles. And then we're going to insert a single second class particle at the bottom, entering at 0, 0, but from the bottom. And we see, so this is the red class particle, the red line denotes the second class particle. And basically, you first sample all of the black lines, and then you insert the red line, and it's only able to move along edges that are still empty. So if you could see in the picture, when it first enters, it's kind of forced to go up for a while because it has no space to go anywhere else. But then later it has some freedom, maybe over here. You could see, you know, it could have chosen to go up, but now it actually is making some of its own choices because once it is in a region where there's some empty edges, it has more flexibility. So what we're interested in is this second class particle. And again, here's a larger scale simulation of its trajectory. And the main theorem that we prove is the following. So if you have this setup with a single second class particle, then what we could do is we could view the y-axis as time. So we could imagine that this is time and the x-axis is space. So at a given time, it makes sense to ask about the position of the second class particle. What is its x coordinate? So we could denote this by xt, the position of the second class particle at time t. And then the speed of the second class particle will just be how much how much it travels over a given time. So xt divided by t. And we show that this speed converges almost surely. So the speed is just 1 over the slope. So just what is the slope of this trajectory, and it converges almost surely to an asymptotic speed or asymptotic slope. And it's a random slope, so it's going to converge to a random variable u, where u is a random variable that takes values inside the rarefaction fan. So it has an explicit density, but what this means is that your second class particle is going to choose a slope in the rarefaction fan, and then almost surely it will just stay along that slope. Okay, and then one more comment about the statement of the theorem is that we prove almost sure convergence, right? But even the weak convergence, so the weak convergence is also something that needs to be proven, and so we do prove that, but the difficulty is to prove almost sure convergence. So proving weak convergence I'll discuss in a minute, but that's based on older ideas, and the strength of the statement is to say that it converges almost surely, right? Because weak convergence wouldn't tell you that every particle actually stays along a given slope, whereas you would get that from almost sure convergence. So what are previous results? The first results in this direction were for TASEP. So TASEP is another particle system, and you could also have step initial conditions for TASEP, and you could insert a single second class particle. And in the 1990s, Ferrari and Kipnis showed weak convergence. And then, like I said, it takes much more work to show almost sure convergence, and that was proven by Mountford and Guiol, and then there were some other proofs given as well. Analogous results have also been proven for the Hammersley process, which is somehow a continuous version of last passage percolation, and also for TASERP, the totally asymmetric zero range process, almost sure convergence of the second class particle was proven by Gonsalves. But these first 3 models are all zero temperature models, or they all have a close relation to models of last passage percolation. So all of those 3 proofs were kind of using similar ideas. The last example where such a result was proven was much more recently by Agrawal, Corwin, and Ghoshal, where they proved almost sure convergence of a second class particle for ASAP. And we could see, from the first result for TASEP in the early 2000s to the result for ASAP, it took, almost 20 years. And the difference is that ASAP is a positive temperature model, and it doesn't have this close connection with last passage percolation. So the tools that were used for the earlier 3 results weren't accessible. And in particular, they needed to develop some new tools in order to prove their results, in particular, some effective hydrodynamic estimates, and also some couplings to control the second class particle. So I want to highlight this last result because the stochastic Six-Vertex model is very connected to ASAP. Like I said in the beginning, actually, ASAP could be viewed as a scaling limit of the Six-Vertex model. So our proof is very much inspired by these new tools that were developed to show convergence for ASAP. And going beyond the almost sure convergence, we're also able to prove a bound on the fluctuations. So you could ask, okay, we take xt and we could subtract off its asymptotic speed, which is given by u, and we want to ask about the fluctuations, and we could show that these fluctuations are bounded by t to the 7 over 9. This is not optimal, so there are results, in particular by Ben, who's in the audience, that show that if you have the stochastic Six-Vertex model with different initial conditions, with stationary initial conditions, then the second class particle should have fluctuations of order t to the 2/3. So in fact, we expect that the 7/9 in our result could be improved to t to the 2/3, but that's not something that we can do with our method. So 7/9 is close to 2/3, but not quite there. And in particular, the methods that we use to get the 7/9 fluctuations, we could also export back to ASAP. So for ASAP, there haven't been results about the fluctuations for the second class particle in this setting, and our methods also could give the same result for a second class particle in ASAP. Okay, so to explain what this result means in a bit more depth, I'm going to introduce a bit of the hydrodynamic theory for the stochastic six-vertex model. Again, just for the case where B1 is less than B2, which is this rarefaction fan regime. And a key idea is that second-class particles are somehow a microscopic way to probe the hydrodynamic, limit of the model. So again, and everything I'm talking about now is basically from either work of Borodin, Corwin, and Gorin, or Amal Agrawal. And again, we're going to view the vertical direction as time. And we could let eta tx denote the occupation variable for vertical edges. So for every vertical edge, there either is a particle there or there's no particle there. So eta tx will be 1 if there's a particle and 0 if there's no particle. And the hydrodynamic limit of the model basically says that if you look in a box and you count up how many particles are in that box, you divide by n squared, then you have some type of law of large numbers, which says that this converges to the integral of some limiting density profile on that box, where the limiting density profile is given by this function rho t of x, which solves some Berger's equation, which is this PDE. And in particular, we could see that this PDE, again, just really depends on kappa. So that parameter kappa is basically what shows up in the hydrodynamic theory. And
So your function phi is linear.
phi,
So a typo, is it k in a row? Or is the x in the denominator row?
is there a typo? There could be.
So
Verify your rows. Shouldn't depend on x, right?
yeah, it must be a row. The bottom must be.
Yeah, maybe it's a row. Okay, yeah. My bad. Anyways, it's not going to come up, so hopefully it doesn't matter too much. But the main point is the next thing, which I think should be correct without a typo, which is the solution to this equation, which is, again, like the pictures we saw before, it's 1 above the rarefaction fan because the limiting particle density will just be 1. It will be packed. It will be 0 at the bottom because there will be no particles there. And then we actually see the function that gives the particle density in the rarefaction fan. Okay, so the hydrodynamic limit is the limit of the occupation variables, but we could also ask about the limiting profile of the height function itself. So the height function counts how many particles are to your right. So you could think of the height function as kind of integrating or counting how many, or integrating the occupation variable because it's adding up how many ones there are. So in particular, we have almost sure convergence of the height function of the stochastic six-vertex model to its limit shape. And the limit shape is given by basically taking that integral of the hydrodynamic limit from the previous slide. So weak convergence of the height function to the limit shape was proven by Borodin, Corwin, and Gorin. But I also wanted to highlight that in a different work with Yerlin, we strengthened that to almost sure convergence. So we have that the height function of the Six-Vertex model converges almost surely to some limit shape. Okay, so now, as I said before, I'll talk about the weak convergence. So showing weak convergence of the speed of the second-class particle is not too difficult, and it basically follows from the hydrodynamic theory. So this follows from ideas of Ferrari and Kipnis, where they did something analogous for TASEP. So what we're going to do, okay, before doing that, again, do people see what I draw here on this side? Okay, so what we're going to do is, instead of viewing the model, so before we were viewing the six-vertex model on the quadrant, and we had step initial conditions. Now, something that we could do is view the six-vertex model on the entire upper half plane. With step initial conditions, that would mean if this is 0, that we would start a particle at every negative position, and we would start no particles at positive positions. But here, this is kind of trivial, because if we start a particle at every negative position, you could show that in the end, for the, on the negative side, things would just be packed. And in the end, you would have particles coming in everywhere on the left boundary. So it would just be trivial over here and you would just recover, you might as well just look at it on the quadrant. But for some of the proofs, we're going to actually, it will be more convenient to work on the line, but with more general initial conditions. So it's shown by Amal Agrawal that you could actually define the six-vertex model on the entire upper half plane. So you have to do some work to show that it makes sense to define it going all the way to negative infinity. But you could start your model with any initial conditions. So maybe, you start a particle here, 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 and so on. And then you could actually sample the model on the entire upper half plane. So for some of the arguments that we're going to make now, it would be more convenient to work in that setting. So we're going to consider two stochastic six-vertex models. One has step initial conditions. So when this setting, step initial conditions is going to mean that we have a particle starting at every negative position. So if this is 0, we're going to have a particle at every negative position, and the other one will be shifted over by 1. So it will also have a particle at 0. So we're going to have two different initial conditions that are just shifted over. And for each of these models, we're going to run the model, and then we're going to compute the expected difference of the height functions of the two models. Now, by linearity of expectation, this expectation doesn't actually depend on how we couple the two models. So we could couple together the two initial conditions however we want. So in particular, we can define two different couplings and compute it for each of them, and what we get should be the same, and it will give us some identities. So the first coupling will be with a second-class particle. So we can imagine that we'll run our model with step initial conditions, however that looks. And then at 0, we'll add in a second-class particle, and it will do something, whatever it does. And now, for the first-class particles, that will give us the six-vertex model with step initial conditions. And if we then also merge the second-class particle, so we uncolor it and make it, the same color as the other particles, then that will give us a sampling for the shifted initial conditions. So the second-class particle is basically just giving us the discrepancy between those two samplings. And with that coupling, what is the difference in the height function of the two models? The height function will only be different if the second-class particle has passed you. So in particular, just the probability that your position is smaller than the position of the second-class particle. Now, the other coupling is even more simple. You sample the model with step initial conditions, and you shift over the entire model by 1, and that's a very trivial coupling. And under that coupling, the difference in the height function, any given position, is just whether there is a particle at that particular position or not. So it's just given by the expected value of the occupation variable at that position. So in particular, this gives us an identity that tells us that the tail of the position of the second-class particle, or the tail of the speed of the second-class particle, is just given by the limit of this occupation variable, which is the hydrodynamic limit. So in particular, if you unpack, now we know that the limiting distribution is given by this limit, and if you write down what that is, you'll get the limiting density that I wrote above. So it's just given directly by the hydrodynamic limit. Okay, but why should the particle converge almost surely, right? So the previous thing is straightforward, but it's just telling us that the distribution of the speed is converging. But how do we know that a single second-class particle will stay along a fixed speed? So here we need a more refined version of the hydrodynamic limit, which is called local equilibrium, which tells you that, after running the model for a really long time, if you look around locally, the distribution of the edges around you are actually, they just look like IID Bernoullis, where the density of the Bernoulli for vertical edges is given by rho, which is the hydrodynamic limit, and the density for horizontal edges is given by this phi of rho, which might be incorrect. So therefore, if you're a second-class particle and you've traveled for a really long time, you're now in this environment that looks like IID Bernoulli edges. And then you're just performing some type of random walk in that environment where you're restricted to the empty edges. And you could compute, I'm not going to write it out, but you could just ask, okay, what's the expected slope of a particle that's traveling in such an environment? And it's straightforward to compute, and you'll see that its expected slope will just be the slope that it's already on. So the idea is that, okay, this doesn't prove almost sure convergence, but it gives some intuition for the fact that, you know, when you're in this equilibrium state, the second class particle is basically going to stay, and it's kind of trapped to stay along its slope. Okay, so okay. So now, as promised, we're going to talk about the speed process, which was the title of the talk. So the speed process is a generalization of what we were considering so far, where instead of just having a single second-class particle, we're going to allow each particle to have a different class. So we're going to have, which ones are the negative ones? 0x, a particle of negative x. Okay, so here we'll have a particle of -1, class -2, -3, and so on. Here we'll have a particle of class 1, 2, 3. Okay, so we're going to allow the particles to have both positive and negative classes. And again, negative classes actually have higher priority because they're smaller numbers. So the particles are increasing in priority if we go up there, and they're kind of decreasing in priority as we go along the bottom boundary. And now each particle has a different class, so it actually makes sense to look at the speed of each particle. Right before, we couldn't really look at the speeds of first-class particles because when first-class particles cross, there's not necessarily a notion of are they crossing or are they bouncing off of each other. But here now, in this picture, each particle has a well-defined trajectory, and you can look at its speed. And in fact, this picture is kind of a generalization of what we had before, because originally we had first-class particles, a second class, and then class infinity. And here, from each particle's perspective, everything above it is kind of higher priority, and everything below it or to the left is lower priority. So almost as an immediate corollary of the previous result, we could simultaneously take the asymptotic speed of every single particle. So this gives us what's called the stochastic six-vertex model speed process. So you could let xt of x be the position of the particle of class x, and then as a process indexed by x, all of these speeds will converge to a limiting process called the speed process. And we kind of have the same family of models that I discussed before. You can construct a speed process for all of those. So for TASAP, this was done by Amir, Angel, and Balco. For TASER, by Amir, Busani, Gonsalves, and Martin. And then for ASAP, by Agarwal, Corwin, and Ghoshal. And the speed process itself has many interesting properties. So in particular, it gives a stationary measure for the dynamics of the multi-class six-vertex model. So basically, we can imagine running the multi-class stochastic six-vertex model with the following initial condition. So now we can allow our particles, classes of particles don't have to be integers, right? Because the only thing that matters when you're comparing the class of two particles is their ordering. So you could allow classes to be any real number. And at position x, we could actually start a particle whose class is distributed like minus u of minus x. If you ignore the negative signs, it's basically the class of the particle at position x will be given by the speed process at x. I don't have so much time to go into this, but I just want to make a comment about how you would prove something like this. So there's these color position symmetries for the stochastic six-vertex model by Borodin and Bufetov, and they basically give some distributional identities between the color or the class of a particle and its position. So basically, it's kind of a tongue twister, but that the class of the particle at position x is somehow equal in distribution to the position of the particle of class x. So it allows you to go between the class of a particle and its position, and then that kind of gives, well, I'm not going to get too much into it, but maybe a hint as to how, you know, here we're taking the speed of the particle and we're turning it into a class. The speed is kind of like a position, so through these identities, it gives a way to go from positions to classes. Okay, so that's one property of the speed process. So then I'll just mention a conjecture, which is that the speed process should converge under certain scaling limit to another process called the stationary horizon, which is a process introduced by Busani as a process that should appear as a universal scaling limit of multi-type stationary measures for different KPZ models. So I'm not going to talk much more about this. So if you're not so familiar with KPZ models, that's okay. Another property of the speed process which has been so okay. There are many properties that were studied for the TASEP speed process in this paper by Amir, Angel, and Valco. And many of those properties are also expected to hold for the ASAP and stochastic six-vertex model speed processes. And some of them were also proven by Martin for the ASAP speed process. So one property which we would also expect to hold in our case is this phenomenon of convoys. So basically, you could look at the speeds of neighboring particles that start next to each other, and it turns out that they often tend to have the same limiting speed. So, with positive probability, two neighboring particles will have the exact same limiting speed. So here's a simulation of, I think, 25 particles, and okay, I don't know if it's so convincing, but maybe you see that they're clustering into different limiting slopes. And we don't prove anything to this regard, but this is just another kind of property that you would be able to study for the speed process, and that should hold for our model. Okay, so for the remainder of the talk, we're going to talk about how to prove the main result, which is the almost sure convergence of a single second-class particle. So the main idea of our proof is to combine two ingredients, and this is also inspired by the proof of the construction of the ASAP speed process. So the two ingredients are effective hydrodynamic bounds. So we're going to need, more quantitative ways to control how close we are to the hydrodynamic limit. And then we're also going to need a way to control second-class particles, or to control the second-class particle locally, because hydrodynamic theory usually only applies when you have a bunch of particles. It's kind of a macroscopic thing. It could tell you how a bunch of particles behave. But here we want to control a single particle. So to control the trajectory of a single particle, we're going to need a way to control a single particle by many nearby particles. So in particular, we're going to control the second-class particle by many third-class particles. And the idea is the following. So we run the model for a long time, and now we expect to be kind of close to the hydrodynamic limit. And okay, I'm again going to imagine that we're on the line because now it will be simpler. So suppose we have our first-class particles at some positions, and then we have our single second-class particle. Let's say it's over here. So what we're going to do is we're going to fill up all empty positions to the left of the second-class particle with third-class particles. So I'll put the third-class particles in yellow. Okay, so now we actually have, if we group together the second and third-class particles, we have a lot of particles. And that's something that we could control with hydrodynamic theory. So the idea is, for this system, we could use our hydrodynamic bounds to show that we're close to the limit shape. But now we want to control this red particle. But how do we know that the red particle didn't just move away from the bulk of the yellow particles? So there we're going to need a way to control the position of the red particle by the yellow particles. So these are the two tools, and now I'm going to go into each one. So the first tool, which are these effective hydrodynamic bounds, they're basically upper and lower tail bounds that tell you how much the height function will fluctuate around its limit shape. So here we have, okay, I think I switched the notation by mistake. So before, the height function had a lowercase h, and now it has a capital H. So we have the height function, and we're going to look along some slope mu. So we're going to pick some slope in the rarefaction fan. So if this is the rarefaction fan given by kappa and kappa inverse, we're going to pick mu in the rarefaction fan. But in fact, mu should be bounded away from the edge of the rarefaction fan by epsilon. So we're going to bound away from the edge because we want our estimates to be uniform over all slopes that we consider. So we're going to consider a slope mu, and then we know that it's by the limit, its limit shape, it should behave like L mu1 times t, right? That's just the limit shape. But we're going to look at the probability that it's much larger than that, and larger than that on the order of t to the 1/3. And then for the other bound, we're going to look at, the opposite, the probability that it's much smaller than expected, but also on the order t to the 1/3. So the first bound we proved with Levy, and the second bound, while our paper was in progress, Ben and Phil Sosway put out a proof of the upper tail bound. And then we also offered independent proof because our proof was using different methods. So yeah, so a discussion of these results. So there's a few things to notice. The first thing is, why are we looking at the order of t to the 1/3 fluctuations? This is because Borden, Corwin, and Gorin showed that the limiting fluctuations on the t to the 1/3 scale are given by the Tracy-Whittem distribution. So they showed if you take t to infinity, then the distribution of the height function on this scale is given by the Tracy-Whittem distribution. Our bounds are, for a fixed t. So we're not going all the way to the limit. We're just looking at a finite time, which is what we're going to need to control the second-class particle. That's the first thing. The second thing, which is a bit confusing, is the notation, the convention I'm using for upper and lower tail. So even though you might want to call the first one is actually the upper tail for H, but I'm calling it the lower tail because it corresponds to the lower tail of the Tracy-Whittem distribution. So often when people are talking about these types of models, there's different techniques that you use for the upper and lower tail. So to match with that convention, it's a bit counterintuitive. And finally, you could see that the upper tail decays more slowly than the lower tail. And I guess some rough intuition for why that's the case is that, you have two situations. Either the height function is much larger than expected or much smaller than expected. For the height function to be much larger than expected, you need many particles to somehow be much larger than you would expect. So that's many rare events that have to occur. Whereas for the height function to be much smaller than expected, you only need the rightmost particle to be smaller, and that somehow blocks the other particles from being too large. So you only need one deviation, so it somehow can occur more frequently. So that explains the mismatch in these exponents, the exponents for the two tail bounds, which are not actually the optimal exponents. So the optimal exponents should be s cubed for the first tail and s to the 3/2 for the second tail, but they're still mismatched. So either way, they are not the same. And in the result from Landon and Sosway, they actually do obtain the optimal tail exponent for the upper tail. So instead of this s here, they obtain a 3/2, and they also obtain, I think, the optimal constants in front. So yeah. And again, this is all part of a recent body of work, which is studying these types of moderate deviation tail bounds for different positive temperature KPZ models. So there's some other works also by Ben and Sosway and Corwin and Hegde studying such tail bounds for a bunch of different models. And also, yeah, and in particular, the lower tail. So somehow the lower tail is more difficult to prove, maybe related to the intuition, where for the lower tail, you need more deviations to occur. Okay, so because of that, I'll just speak briefly about how we prove the lower tail, just a small part of the proof. So we use this identity from Borden and Olshansky, which connects the stochastic six-vertex model to the Meixner ensemble. So the Meixner ensemble is a determinantal point process. So it's basically a random point process. And the left-hand side of this identity is what's called the Q-Laplace transform of the height function. So it's basically some function, we look at the height function at position m comma n, and you multiply it, you take q to that power, and yeah, you could see this, this transform, and it tells you that this expectation is equal to a different object, an expectation over all the holes in the Meixner ensemble. So the Meixner ensemble is a bunch of points, and the holes are just, the positions that don't have points. And if we look at a product over all the holes in that ensemble, we get another expectation that's equal to the Q-Laplace transform of the Six-Vertex model. And somehow this allows us to reduce the tail of the lower tail for the height function to studying the tail of just the smallest, so from this product, we can drop all the terms except the smallest hole. And then we get just a tail bound for the smallest hole of the Meixner ensemble. And since the Meixner ensemble is a determinantal point process, that means that its correlation functions are given by some Fredholm determinants, and it has a very nice algebraic structure. So reducing our problem to studying the tails of the particles in the micro ensemble opens up a lot of other tools, and it involves a lot of contour analysis and other fun stuff that I'm not going to get into. What time do I go until 4?
Sorry.
Okay, whatever. I think I'm almost finished. Yeah.
So can you see with this formula what's supposed to happen like the deep lower tail, like when you like at some point you transition from the cube, presumably, in the deep lower tail of the stochastic Six-Vertex. Do you know what happens there?
I'm not sure. What do you mean, the transition?
Like, so that, what I would guess is, that your lower tail is like e to the negative s cubed up to some point. And then there should be some change, maybe to 5 paths, but maybe something that is specific to the stochastic Six-Vertex model. I'm not sure.
I see. I'm not sure, but there is a work that will be coming out soon by Promed and Guillaume. And I think they're studying very exactly what happens for this tail. Like they're going to use this entire product, not just the smallest particle. So they might be able to see that. Yeah. But our analysis I don't think is fine enough to see that. Okay. So going to the other part of the proof where we need to control the second class particle by third class particles, we prove the following result, which we call geometric stochastic domination. So basically, it's the same setup that I have here. We're going to have a bunch of first class particles, and we're going to have a single second class particle. The only difference is we don't need all the third class we don't need to fill up every space with third class particles. We just have to imagine that there are some third class particles that are all to the left of the second class. We could fill up all of them, but we don't have to. And then what the result is saying is, okay, run your process for some amount of time, and then count how many of the yellow, at a later time, maybe, we still have our first class particles, and now maybe some of the yellow particles have overtaken the red particle. So some of the yellow particles will now be to the right of the second class particle. So we want to show that not too many of the yellow particles have actually passed to the right of the red particle. So what we show is that if you look at time t and you look at the number of third class particles that have overtaken the second class particle, it's dominated by a geometric random variable with a parameter b1 over b2. So that was the other important parameter in our model. And in particular, this geometric bound doesn't depend on time, and it doesn't depend on the number of third class particles. So it really gives us good control over how many third class particles have overtaken our second class particle. And I just want to compare with what they did for ASAP. So to construct the ASAP speed process, they also needed some way to control the second class particle. And what they used was a coupling by Rizza-Conlu that goes back to the 90s, which we didn't have available for us. So I just want to compare the two results. So for that result, you also have the same setup with a second class particle and a bunch of third class particles to the left of it. But what they show is that you could pick a uniform third class particle, and a uniformly chosen third class particle will stay to the right of the second class, to the left, will stay to the left of the second class particle. So in particular, it allows you to control a second class particle with a uniformly chosen third class particle. Now, the difference between the two results is that, we're getting a much stronger control because we're saying only a geometric number have overtaken the second class particle. Whereas they're saying, with the Rizza-Conlu result, it's saying a uniformly chosen third class particle has not yet overtaken the second class particle. So it's telling you how many have remained and have not yet overtaken. And also, this uniformly chosen particle, that control gets much worse when you increase the number of particles that you have. Okay, so you might ask, so Rizza-Conlu's result proceeds with a coupling, and you could ask if you could construct a similar coupling for the Six-Vertex model. And in fact, Ivan Corwin presented such a coupling, but it only works for B1 less than 1/2, which is kind of, the regime where you can go from Six-Vertex model to ASAP where, you know, B1 is small. And it's not possible to extend that coupling for all parameters B1 and B2, which is why we needed to develop the other result. Now, again, kind of the same with our fluctuation result. This result can, I mean, our result can also be exported back to ASAP to give a stronger version of this coupling. Okay, so I guess, oh, yes.
Okay, so your result implies the existence of a coupling where you choose like an index on your third class particle according to this geometric random variable, and then you know almost surely this third class particle stays to the left of the second class particle. But do you get like an interesting explicit coupling, or is it?
But do we have a geometric that stays to the left? Because we're showing that at most a geometric overtake, so that's
Most of the
different.
geometric overtake, but it's like
So less than a geometric, so
there's like
the
so I'm asking like for like a you pick okay, very clear. There exists some explicit coupling. So basically, like Rezakono's coupling is there's some coupling of the uniform random variable with the entire process, such that almost surely the uniform label is less than or equal to your label, and the coupling is presumably like maybe.
Right. Yeah. Sure.
you can do the same thing if you replace a uniform label with like a geometric.
But the uniform label and geometric.
Like abstractly, there is such a coupling. I'm just
wondering
if you get like
we don't obtain an explicit coupling, but for the version that I've created, there is an explicit coupling, but it only works for some parameters. So yes and no, but we don't know how to get such an explicit coupling for our version, but maybe there is one. Yeah.
I can ask.
Yeah. Okay, so just to summarize, we've shown that a second class particle in the Six-Vertex model converges almost surely to an asymptotic speed. And this allows us to construct the Six-Vertex model speed process. We've also bounded the fluctuations by, shown that they're not more than t to the 7/9, but in fact, this should be possible to improve to t to the 2/3. And there are many more properties of the speed process that are open to study, including the convoy structure and also proving that it has some nice scaling limits to objects like the stationary horizon. And here are just some of the references that I had in my talk. Thank you very much. Are there any questions?
How universal the convoy structure is?
So we were talking about this earlier, so maybe Duncan could say more in terms of the directed landscape. But I think it seems pretty universal because at least we have it for these models.
Should be universal even if you're not nearest, like non-nearest neighbor exclusion should have the same. Yeah, but convoy structures also.
Yeah, like the convoy structure.
For like non-nearest neighbor exclusion.
Non-nearest neighbor.
The same convoy. Oh, okay.
And that will converge. I mean,
is it proved or
is it non-nearest neighbor exclusion?
It's very difficult to prove the convoy. Like for TASAP, they use like some queuing interpretation by James Martin of the stationary measures. And then already once you go to ASAP and Six-Vertex model, it gets very difficult to study. I think there's some results for ASAP, but it already gets very hard. So I would imagine that it becomes even harder if you go to.
Look at the convoy structure and scaling window, where you see the directed landscape, it converges to the shock measure. In any model where you have convergence of the areas, you should be able to show that. It might be some technical work, but it should be. I think it's probably harder for positive temperature models. I think it might be immediate for colored TASAP. But I don't even know. So can you compute? Do you have like enough? Because I think in colored TASAP, the probability of the speed of the particle at 0 and particle at 1, the probability of those speeds are equal as like 3/8 or something.
Right. They computed, yeah.
Can you do this for do you have like an exact number?
I'm not 100% sure if that was done for ASAP, because I know that in the TASAP speed process paper, they make a bunch of conjectures and they say, conditional on some results being proven later, we have this result for ASAP as well. Then there's this paper by James Martin that does some stuff for ASAP. So it may or may not have already been proven kind of by having those conjectures earlier. So I'm not 100% sure. That was
Maybe I'll ask, I think this is a related question. Do you know if so you have like a speed process for ASAP,
right.
which is, and then you have a speed process for the stochastic Six-Vertex model. Is that, so by a speed process, it's like a sequence of identically distributed random variables indexed by Z with some funny and complicated correlation structure that results in these convoys inside. Is the ASAP one like a simple transformation of the stochastic Six-Vertex model speed process?
Yes. So yes, so I didn't get into this, but actually conditional on one thing which we didn't prove yet, but we're going to add to the paper. So you have to show that that the stationary measures for the stochastic Six-Vertex model, there's a unique ergodic stationary measure for the N class model. And if you could show uniqueness, then you can match. There's some recent results by Leo Petrov, Matthew Nicoletti, and Amol Agrawal that give explicit constructions of such stationary measures for both ASAP and the Six-Vertex model. So if you know uniqueness, you could kind of match, and then you can show that those measures are actually the same. And
same up to like the trivial scaling and everything, replacing like the uniform.
Exactly. So we will prove that, and then we'll add it to the paper maybe in a week or so. And then, yeah, we will have that result.
Okay.
Yeah, once we prove the uniqueness. Yeah.
If you have the right moderate scales.
So it's just about balance. So it's really just a fault in the argument that we use where we're taking some approximation, we're taking some sequence of times where we are approximating the height function with the hydrodynamic limit. And then we also need to like control between those times. So there's some trade-off. So I think it's just an artifact of the proof. There are other sequences of times that you could choose where you would see that the fluctuations should be of order t to the 2/3, but they just won't, you won't be able to actually prove the results. So it's just somehow balancing different effects in the proof, but I think you would need a different method to get the 2/3.
So thank you. Yeah, let's see. Wednesday. Okay, now what is Other aperture before.
I think this guy's watching. Hindy, what did you tell me? I know, you can turn it off.
We could talk, do either.
Is that okay? Okay.
We could talk yes. And then. That's probably good. Yeah.
One needs to be like coordinating. I'm just gonna